The court is now in session.
Hi, I'm Arushi.
Hi, I'm Michelle.
And I'm Mehak Zaveri.
I'm Janani.
Hi, I'm Somesh Agrawal.
And I'm Monsuin Elisto.
Today, we will present our proposed reward database system for U-Tweet Face and show why it satisfies the requirements set by CEO Taro Amochi. U-Tweet Face is a merged social media and shopping platform where users earn rewards through activities such as making purchases, watching videos, commenting, creating content, playing games, and sharing posts. Some of these rewards should be permanent, while others should expire after a short period of time. The system must also support lucky draws, multipliers, and product promotions, while remaining fast and flexible. These requirements come directly from the project brief.
So this is not just a storage problem. It is a dynamic database design problem. User balances keep changing, tiers can go up or down, temporary points can expire, promotions can affect many users at once. That means our design has to support both fast access and fast updates without losing correctness. Our report frames these needs as 10 core KPIs that the system must satisfy.
So let me get this straight. All users earn points directly?
Yes, Your Honor. Purchases, videos, comments, games, referrals.
And all of this changes constantly?
Exactly, which is why this is not just a storage, it is a dynamic system problem.
Fine, let us test your so-called KPIs.
Before choosing any data structure, we first identified what the system must actually do. KPI 1 is efficient user record storage. Every user has a unique ID, point balance, tier status, and a collection of point entries. Lookups, insertions, and deletions should run in expected constant time and scale to 1 million of users. KPI 2 is support for multiple point types. Some points are permanent, such as purchase rewards, while others are expiring engagement points. Each point entry may need a source, timestamp, and expiry time. And expired points must be removed without breaking the total balance. KPI 3 is automatic tier management. Users belong to one of 4 tiers, and whenever their total points cross a threshold, the system must update their tier quickly. The report specifies that the tier logic itself should be a simple constant time function of total points. KPI 4 is efficient range queries. The system must be able to quickly find all users whose points fall within a given range, for example, lucky draws. The target is log n plus k, where k is the number of return users.
If I ask for one user, how fast?
Expected O1,
And for millions of users?
still O1.
And do the points expire?
Yes, and we remove them without scanning all the users. KPI 5 is tier filtered querying. The system should be able to retrieve users from a specific tier or combine tier and range filters without scanning the entire database. In our design, tier is treated as a function of total points, so tier queries reduce naturally to range queries. KPI 6 is bulk point multiplication. If a promotion multiplies the points of all users in a chosen range or tier, the system must update those users, re-index them, and handle any resulting tier changes efficiently. Our target is OKC login. KPI 7 is direct tier override. For certain promotions, the system should be able to upgrade a single non-platinum user directly to platinum in logarithmic time while updating the main index. KPI 8 is a point expiration handling. Since temporary points expire, the system must efficiently find the next expiring entry and remove expired entries in batches without scanning all users. The report models this using a min heap on expiry timestamps. KPI 9 is extensibility. The design should be modular enough to support new promotion types later. such as top K users or interactive user detection, without rebuilding the entire system. KPI 10 is consistency. During concurrent operations, point, accruals, and bulk promotions may happen at the same time, so design must consider how to keep balances and indices correct when operations overlap. This is important because stale or inconsistent data would undermine the entire reward system.
Let's make this real. If you buy something, you get P points. But if you binge something, you earn T points. But T points expire.
So users lose points?
Yes, which means they can also lose tiers. Now that the requirements are clear, we move on to our proposed point system. We use a 2-point system, permanent points or P points, and temporary points or T points. This is the exact structure presented in our report. P points reward high-value actions and never expire. And in our design, users earn 1 P point per $1 spent. 50 P points for original video content that exceeds 1,000 views, and 100 P points for referring a new user who completes registration and makes a first purchase. And finally, 10 P points for completing a verified product review with photo or video evidence. T points reward regular engagement and they do expire. So in our design, 1 T point for 5 minutes of watching videos and they expire in 30 days. 2 T points per comment, which expires in 14 days. 5 T points per consecutive daily login, which expires in 7 days. 3 T points per in-app game session and expires in 21 days. And finally, 5 T points per external share, which expires in 14 days. This dual system is important because it rewards both high spending and engagement. It also creates the technical need for expiration management, which daily influences our data structure choices.
Every user belongs to exactly one of 4 tiers based on total points. Our report defines the thresholds as Bronze, which is 0 to 999 points, Silver, which is 1,000 to 4,999 points, Gold, 5,000 to 19,999 points, and Platinum, which is 20,000 points and above. Tier transitions happen automatically whenever a user's total balance changes. That means users can move upwards when they earn more points, but they can also be demoted when temporary points expire. Because of this, tier updates cannot be treated as a rare event. They are part of normal system operation.
So, Your Honor, we did not just build one system, we built 3. Hash table, AVO tree, and min heap, all together.
3 structures sounds inefficient.
Your Honor, if the question is find this exact user, we answer instantly, O1. Anything else would be slower.
So, to satisfy all of these requirements, our system uses 3 main data structures working together. 1. A hash table as the primary user store. 2. A global augmented AVL tree indexing users by total points. 3. A global min heap managing expiring temporary points. The key principle in our system architecture is that the hash table stores the full user record, while the AVL tree and min heap store only the information needed for efficient indexing. The report's architecture diagram shows exactly this interaction. All indexing structures refer back to the users via user IDs and the hash table for full record access.
Our first structure is the hash table, which serves as the primary user store. Each user record contains user ID, username, permanent point balance, total non-expired temporary point balance, cash total points, current tier, a linked list of all temporary point entries, and a purchase history. We chose a hash table because the most frequent basic operation in the system is direct lookup by user ID. The report explicitly compares this against the alternatives like an AVL tree by ID and a sorted array. The hash table gives expected O1 lookup and amortized O1 insertion and deletion, whereas ordering by user ID gives no real benefit for our problem. In other words, if the question is find this exact user, then the hash table is the best.
And this tree?
This is where it gets interesting. If you want rankings, ranges, and lucky draws, this tree does all of it. Our second structure is an AVL tree, indexed by total points. This structure is responsible for ordered operations such as range queries, ranking, counting users in ranges, and repositioning users when the balances change. We specifically used an augmented AVL tree. In addition to the standard AVL fields like key, child pointers, parent pointer, and height, each node stores a subtree size value. This turns the AVL tree into an order statistic tree, which supports efficient rank-based queries. The report also explains how subtree sizes are maintained during updates and rotations. We chose an augmented AVL tree because a plain hash table cannot support efficient range queries, and a sorted array would make updates too expensive. The report compares these options directly and concludes that the augmented AVL tree is the best overall choice for balancing fast range queries with frequent updates. We also handle duplicate total points by storing a linked list of user IDs at each AVL node, since multiple users may have exactly the same total points.
And this, Your Honor, is the most dangerous part.
Dangerous.
Because if we fail here, expired points stay, and the entire system becomes wrong.
Our third structure is the global mean heap, used for expiring T points. Each heap entry stores expiry time, user ID, and point value. We chose a mean heap because the system always needs to know which temporary point expires next. A mean heap gives big O1 access to the minimum expiry time and big O log P insertion and extraction, where P is the heap size. The report compares this against sorted arrays, unsorted arrays, and AVL trees, and the mean heap is the best fit for this requirement. We also deliberately use one global heap, not separate heaps for each user. If each user had a personal heap, finding the globally quickest expiry would require scanning across users, which would be inefficient. A global heap avoids that and gives direct access to the next expiry event.
Okay, so now I'm going to walk you through how our system actually operates using the pseudocode in section 6. So let's start with add points function. Whenever a user earns points, we look up the users in the hash table, then update either the permanent or the temporary points based on the inputs that we are given. So if it's a temporary point, we create a new entry with the expiry time, add it to the users list, and insert it into the min heap for tracking expiry. After that, we recompute the user's total points, update their position in the AVL tree, which takes O log n time, and finally update the tier. So overall, this operation ensures that all three structures stay consistent after point addition. Okay, so let's move on to process expired points, which handles expiring the T points. As mentioned before, we use a combined approach for expiring points, which is the lazy one and the eager expiration technique. And this is how the function actually runs. So we continuously check the top of the min heap, which always gives the earliest expiry, as you can see here. And then if the entry has expired, we remove it. That's it. Then we look up the user in the hash table, and then subtract the expired points, updating their total, and reposition them in the AVL tree. An important detail here is the lazy validation. So for example, the database admin can change some part of the T-point list if there was some error or some problem in the database, right? So this has nothing to do with the lazy expiration. This is lazy validation, completely different. So if it's a stale entry, right, if it's already in the heap, but it's not in actually the user's T-point list, then we have to check for this, basically. And after that, yeah, so that's about it for process expired points. So what's determine tier? This is a helper function. It updates the tier updates are handled by a very simple function like this. Yeah, so it just checks if points are more than 20,000, it's a platinum. Else if it's less than 5,000, it's more than 5,000, it's gold, silver, and bronze. You get the point, right? This runs in O1 time and just users. This is used for the user after they move around the AVL tree. Tier updates themselves are constant time operations. All right. So what's the range query function, which it is also powered by the AVL tree. This is the power of the AVL tree that we were talking about before, right? This all allows us to find all the users whose point lie within the range, low and high. So this is the input. These are the input for the functions. We do this using recursive traversal, only visiting relevant parts of the tree and collecting matching users. This gives us a time complexity of O log n plus k, where k is the number of results that are obtained. This is extremely efficient and supports features like lucky draws, tier-based filtering, etc. So this is a very important function that we need to understand. Yeah. We have given more examples here, and you can read a bit more in the report. So what's range multiply? So this is the basic function that we use for lucky draws. Now, This applies are multiplied to all users in a given range. So what are the steps to it? First, we process expired points to ensure correctness. Then we run a range query to get all users. For each user, we update both p points and t points. Recompute totals, update AVL position, and update their tier at the end. Yeah. So this operation runs in O log n plus k log n. Why? Process expired point runs in log n, then log n plus k. Then for every user that you have got, range query runs in O log n plus k. And then for every user, there's k users in the user ID section. And then for k users, you go through each one of them, and then you update them in the global AVL tree. So this one is just log n again. So it's log n, k log n. Everything else is constant. This one is log n. So k times log n, basically. Yeah, that's it. So what's product permission upgrade? This is the last part of our pseudocode section. So this is used for promotion. We retrieve all the buyers of a product. So we assume we have a hash table called purchase index that has all the product IDs and as the IDs as the key of the hash table, and the buyers as the values. So after we obtain the buyers for each of the products, we filter out all the platinum users like this. And then if eligible is empty, we just return null. And next, we directly boost their points to 20,000 and update their global AVL tree position after randomly selecting them. Yeah. Then we return the winner ID. So the time complexity for this OB log plus n. So overall, section 6 shows how the hash table ensures fast access, the AVL tree maintains order and supports queries, and the min heap handles time-based expiration. Together, these structures allow us to support all system operations efficiently while keeping everything consistent.
Okay, let us test out the system. We have user A who has 950 points. She goes shopping.
Processing purchase plus 100 points.
Total 1050.
AVL tree updates.
Tier recalculating is now silver.
Promotion accepted.
Yay!
Now that we looked at some of the structures that we've implemented, let's see why we didn't implement some of the rest. We didn't just use a hash table because it wouldn't effectively do the range queries. It would have failed the KPIs 4 and 5. We didn't just use a sorted array because although it would do the queries fast, the frequent point updates would require expensive shifts, making the updates too slow. We didn't use a regular binary search tree as it doesn't guarantee a balanced performance in the worst case, and thus we used an AVL tree instead. We didn't use a per user heaps because that would make the global expiry tracking ineffective. A single global min heap solves this cleanly. So our design is not 3 random structures placed together. Each one exists because it is the best answer to a specific type of operation.
So, Your Honor, we would like to introduce a new feature which is called the Community Challenge Rewards. Unlike normal promotions that reward individuals, this system focuses on collective achievement. This idea is simple. Instead of just one user winning, the entire community works together towards a shared goal.
So this depends on multiple users, not just one.
Exactly. In fact, the challenge only succeeds if there's enough participation across all tiers: bronze, silver, gold, and platinum. This ensures there's no single group that dominates the challenge, and everyone's contribution actually matters.
Each challenge is defined by a few parameters. There's a theme, like eco-awareness week, a fixed duration, say 7 days, and a collective target, for example 1 million points. On top of that, we also require minimum participation from each tier, so the system remains balanced.
During the challenge, users earn something called C points or challenge points. These are completely separate from permanent or temporary points. For instance, in the eco-theme challenge that Janani mentioned, users might earn points by watching environmental-related content, by buying environmental-friendly products, or simply sharing sustainability tips.
What happens if they actually reach the target?
If both conditions are met, the total point and the tier quotas, the challenge is successful and everyone who contributed gets rewarded. All users receive a 1.1 times multiplier on their total points, while the top 10% of contributors get an additional boost. On top of that, lower tier users who help meet quotas receive extra permanent points, which encourages participation from all levels.
And if they fail?
We still reward participation. Every user gets 50 temporary points, even if the challenge does not succeed. This way, users are not discouraged and are more likely to join future challenges.
From a system perspective, this is implemented efficiently using our existing design. During a challenge, we create a temporary hash table that tracks each user's C points, allowing fast updates in constant time.
At the end, we simply iterate through this table to calculate total contribution and check tier participation. If challenge succeeds, we distribute rewards using our existing update system, including AVL readjustment and tier recalculations.
To identify the top contributors, we use a heap structure, which allows us to efficiently extract the top 10% without scanning everything repeatedly.
Refer to the report for more details.
What makes this feature powerful is not just the rewards, but the behavior it creates.
Users now have a reason to encourage other users to participate, which leads to organic growth.
It transforms the platform for a reward system into a collaborative ecosystem.
This system doesn't just store data, it understands behavior, it adapts, and it scales. For the case of the UPID phase system, I rule.
So beyond just technical performance, our system also contributes to real-world impact. Firstly, it supports sustainability by encouraging responsible consumption. For example, through community challenge, users can earn rewards by engaging in eco-friendly activities like watching sustainability content or choosing greener products. Secondly, our system is computationally efficient. By using data structures like AVL trees and hash tables, we reduce unnecessary processing, which helps lower energy usage at scale. We prioritize inclusivity. The dual point system ensures that users who cannot spend money can still progress through free activities like watching videos or logging in daily. This prevents the platform from becoming pay to win. Additionally, our system is culturally and geographically inclusive, allowing challenges to reflect global events and ensuring accessibility even for users with slower internet connections. Overall, our design is not just efficient and scalable, but also sustainable, inclusive, and adaptable for future growth.